Welcome viewers. If we are given the task to find out the resistance of a given wire, say this wire, then we can find it out by using the formula R equals rho L by A. For this purpose, we will require to measure its length. We can measure by using a meter scale. We will require its cross-sectional area. If the wire is very slim, then we can measure it by using a screw gauge. But the real problem is to find out the value of rho. Rho is the resistivity or the specific resistance, which we can't find merely by looking at this wire. So, today we will learn about an instrument with the help of which we can find resistance without knowing resistivity of material. The instrument is available in the physics laboratory of your school. The name of the instrument is meter bridge. Here we can see an image of a meter bridge. The main part of a meter bridge is this wire AC, which is a 1 meter length wire, and it is a resistance wire which may be made up of nichrome, magnin or constantin. The two ends A and C of the wire are held out between these two thick metallic strips. One strip is here and we can see the second strip is here. Between the other two ends of these two strips, we can see an I-shaped thick metallic strip. Let us number this strip as strip 3, and we can see the gap between these L-shaped strip and I-shaped strip here, and we can see the gap here also. In these two gaps, we can attach the resistors. At the midpoint of this I-shaped strip, we have a terminal named as B here. With this terminal, we have connected a galvanometer, and the other end of the galvanometer is connected with a jockey. The jockey is a metallic rod whose one end has a knife edge and the other end is connected with the wire to make electrical connections. Here in this gap, we have connected a resistor R, which is an unknown resistor, and on the other gap we have connected S, which is a standard resistor. Across the wire AC, a battery is also connected, and the battery is also provided with a switch. The jockey can be moved along this wire AC. Let us suppose that there be a point D where the jockey is connected with the wire. If this length from A to C is L, then the resistance of this length can be written as rho Cm into L. Here rho Cm is a quantity which is defined as the resistance per unit length of this wire. In this case, the resistance of the portion DC can also be written, as we can see that its resistance, as we can see that its length is 100 minus L centimeter. So, its resistance will be rho Cm, that is resistance per unit length, multiplied by 100 minus L. So, in actual practice, while trying to find out the value of resistance R, the jockey is being moved from point A to C, and remember, while moving the jockey, we have to tap it on the wire and it is never being slided on the wire. While trying to find out the value of the resistance R, the jockey is being tapped across this wire AC, and we never slide the wire since it can change the cross-sectional area of the wire. Let D be the point where galvanometer shows 0 deflection. Now we can compare this arrangement with a balanced Wheatstone bridge, and we are aware that if there is no current in the galvanometer arm in a Wheatstone bridge, then the ratio of this resistance to this resistance is same as the ratio of this resistance to this resistance. So, applying that condition, we can write that resistance of arm AD divided by this resistance R will be the same as resistance of the length DC divided by the resistance S. As we have already seen that if this length is L, then its resistance is rho Cm into L. So, our AD can be written as rho Cm into L, and R is the unknown resistance which has to be found out, whereas RDC is the length of this resistance, where RDC is the resistance of this length, which is rho Cm 100 minus L divided by S. You can see that these two terms will be cancelled out, and we are left with L upon R equals 100 minus L upon S. From here, R can be written as Ls upon 100 minus L. S is the standard resistance, so we are aware of its value. L is the length measured here, and 100 minus L is the length on the other side. So, by using this formula, we can find out the value of the unknown resistance. By choosing different values of S, we will be finding different values of L, and hence we will be calculating the resistance again and again. If the jockey is moved along the wire, then there will be one position where the galvanometer shows no current. In this position, the bridge is said to be balanced, and it is the principle of meter bridge. So, the principle is, it is based on the principle of a balanced Wheatstone bridge. Let the distance of the jockey from the end A at the balance point be L1. The four resistances of the bridge at the balance point are R, S, rho Cm L1 and rho Cm 100 minus L1. The balance condition is R by S equals rho Cm L1 upon rho Cm 100 minus L1, which equals rho Cm, which equals L1 upon 100 minus L1. Thus, once we have found out L1, the unknown resistance R is known in terms of the standard resistance given by this equation. By choosing various values of S, we would get various values of L1 and calculate R each time. An error in measurement of L1 would naturally result in an error in the measurement of R. It can be shown that the percentage error in R can be minimized by adjusting the balance point near the middle of the bridge, that is when L1 is close to 50 centimeter. This will require a suitable choice of the value of S. Now, to test that how much we have learned, let us solve a few application based problems. A resistance R to be measured using a meter bridge. Student chooses the standard resistance S to be 100 ohm. He finds the null point at L1 equal to 2.9 centimeter. He is told to attempt to improve accuracy. What should he do? As we have just seen that in order to minimize the error, the balancing point should be close to 50 centimeter mark, and here the student is getting the balancing point at a length of 2.9 centimeter. It means the ratio of these two resistors is very large. So, in order to get the balancing length near 50 centimeter mark, we will have to decrease the value of S, so that the ratio will be close to 1:1 and we will be getting the balancing point near the middle point. Second question is, what happens if the galvanometer and cell are interchanged at the balance point of the bridge? Would the galvanometer show any current? Answer to this question is that it will not affect the balance point at all. It is because the bridge is still balanced, and hence there will be no current in the galvanometer. Okay viewers, so a meter bridge helps us to find out an unknown resistance. What if we try to verify the value of a known resistance? Next time when you visit your physics lab, try to verify the color codes value of a carbon resistor with the experimentally calculated value. So now, moving ahead, if I ask you to name a device to measure potential difference, then your answer may be a voltmeter, But a voltmeter does not measure the exact value of a potential difference. The device which can measure the exact value of potential difference is potentiometer. Now we will learn about a potentiometer. In a potentiometer, we have a wooden platform shown with brown color in this diagram. Over this platform, at one of the wider end, a wooden meter scale is fixed. This is the wooden meter scale. Now the most important part, it has a long piece of uniform wire which runs multiple times along its length. This is the wire which runs in this diagram, it has run 4 times across the length. Two adjacent ends of the wire are connected with a thick metallic strip. You can see 1, 2, 3 meter length, and these ends are connected with thick metallic strips. One we can see here, second one is here, and third one is here. A standard cell is connected across it. Here is the cell. The cell is also provided with the rheostat so that we can control the current, and to switch on or off the cell we have this key K1. Since the wire is uniform, the potential difference between point A and at any point at a distance L from A is directly proportional to the length. As we can see that this battery has applied its voltage across this wire AC. Wire being uniform in cross sectional area, longer is the length, longer will be the potential difference across it. So we can write V is directly proportional to L, which can also be written as V equals phi times L, where phi is a term which is known as the voltage drop per unit length. This is the working principle of a potentiometer. Let us number this equation as equation 1. The potential difference across length L of a potentiometer wire of uniform cross section area is given by this V equal to phi L. By using potentiometer, we can compare the EMFs of two sources. Number 2, we can find the unknown EMF, and we can also find the internal resistance of a cell. First, we will understand the comparison of EMFs of two sources. Let these two be the two cells E1 and E2, whose EMF are to be compared. Now, these cells are connected to a point A. Let this be the first cell, and at the point A itself, the second cell is also connected. The other ends of the cells are connected to a two-way key. And the end of the two-way key is connected to a galvanometer, which in turn is connected to a connection wire, which is joined with the jockey, and the jockey is again free to run along this wire. Let us name these cells as E1 and E2. To keep the first cell in the circuit, first we plug in this key. So only the cell E1 is in the circuit, and in this case let the balancing length be L1. Let this length be L1. Then we can say that the EMF of the cell E1 is balanced by the voltage across this length L1. And as from the principle of the potentiometer we are aware that the potential drop across any length L is phi L. So in this way we can write that EMF E1 is balanced by the voltage phi L. So for the first cell we can write E1 equals phi times L1, where L1 is the balancing length for the first cell. The same process is to be repeated for the second cell also. In this case, now we will plug in the second cell into the circuit, and we will move the first cell out of the circuit. By doing this, we have introduced the second cell in circuit, and let the balancing length this time obtained is to be L2. So again the cell So again the EMF E2 of the cell is balanced by the voltage drop across that length. From the principle of potentiometer, that voltage is phi times L2. So for the second cell, E2 is phi times L2. Let us number this equation as equation number 3. By dividing these two equations, we can compare the EMFs of these two cells. So 2 by 3 gives E1 by E2 equals L1 by L2. Let us number this equation as equation number 4. If E1 and E2 are the EMFs and L1 and L2 are the balancing lengths of the two cells, then E1 upon E2 is equal to L1 by L2. Using this equation, we can find out the unknown EMF also. For that, one cell has to be the standard cell. Suppose we are aware of the EMF E2, then obviously we can find the EMF E1 also. Here it is important to note that no current is drawn from the cell in calculating EMF, as galvanometer has shown zero deflection. That is why we get exact value of EMF. We can also find internal resistance of a cell with the help of potentiometer. For that, we will have to make minor changes in this circuit. So in order to find the internal resistance of a cell, what we have done is that we have replaced the second cell by a resistance box. We have also attached a key, and the two-way key has been removed now. Now we will follow the same steps as we did for the comparison of EMFs of the two cells. In the first case, this key is being switched off. Now the cell E is in the circuit and the balancing length is obtained. Let the balancing length is L1, and again the EMF of the cell is balanced by the voltage drop across its length L1. And as the voltage drop is phi L, so we can say that the EMF is balanced by the voltage phi L. So the EMF E is balanced by phi L1. Here L1 is the balancing length when only cell is in the circuit. Let this equation be equation number 2. Now resistance box comes into picture. Now we switch on this key and we again obtain the balancing length. This time the balancing length comes out to be different. Let us name this balancing length as L2. In this case, what happens that actually galvanometer is not drawing any current, which is evident from the galvanometer showing zero deflection, but some current is still drawn from the cell E, since this circuit is still complete. So in this case, the cell is still giving some current I in the circuit. If the resistance taken out from the resistance box is R, then what we are balancing here is not the EMF, actually it is the terminal potential difference. So what we are balancing, let us name it as V, and as it is balanced by the length L2, so we can write V equals phi L2. Let this be equation number 3. By dividing these two equations, we get E by V equals L1 by L2. From the relationship between the EMF and the terminal potential difference, we are aware that E can be written as V plus IR. So writing E as V plus IR, we have V plus IR upon V equals L1 by L2. In this expression, I is the current drawn from the cell, whereas small r is its internal resistance. If we distribute this V with the first term and with the second term, then we will get 1 plus IR upon V equals L1 by L2. We are also aware that this capital V is equal to I into the current drawn. We are also aware that this capital V is equal to I into R, that is the resistance taken out from the resistance box. So using that, it becomes IR upon I into capital R. I being cancelled out from this expression, we can find the expression for small r, which is L1 by L2 minus 1 multiplied by capital R. So, by using this expression, we can find out the unknown internal resistance of the given cell. To test and improve our understanding of potentiometer, let us solve a few more questions. So, regarding this diagram, the first question is that what is the purpose of the high resistance 600 kilo ohm? Here, this is the standard cell and this is the test cell for which we are testing the circuit. Once when we are away from the balancing point, then galvanometer will be carrying some current. Since galvanometer is a delicate and sensitive device, so to prevent it from high values of current, we have put this resistance 600 kilo ohm in series with the galvanometer. So, the purpose of 600 kilo ohm resistance is to prevent the galvanometer from high values of current. The second part of the question is that is the balance point affected by the high resistance 600 kilo ohm? This time the answer is no. Actually, once when we reach the balance point, then in any case no current is flowing through the galvanometer. So, 600 kilo ohm has no role to play to control the current. Third question is the balance point affected by the internal resistance of the driver cell? In this case, this is the driver cell, and if we imagine that its resistance is increased, then the current sent by this cell along the wire AB will be less, and since the current will be less, so the potential drop per unit length will also be less, and hence the balancing length will obviously be affected. The next question about this diagram is, would the circuit work well for an extremely small EMF of an order of a few millivolt? If not, what changes are required to be brought? If this test cell is of very small voltage, say just a few millivolt, then although we will be getting the balancing length, but since we are aware that voltage drop is directly proportional to length, hence the balancing length will be very close to A. It may be a few millimeter or even it may be a fraction of millimeter. So, to measure that small length will be an extremely difficult job. So, this combination is not suitable to measure very small voltages such as the voltages of the order of millivolt. So, what we can do to measure these voltages? For this, we can try a few things. We can replace this cell by a cell of smaller voltage is one thing. We can introduce a series resistance with this cell so that the current sent through the wire AB will be less, hence voltage drop per unit length will be lesser, and we will be getting more balancing length with that small millivolt cell, so that the length will still be measurable and we will be able to measure it. Now, some work for our viewers. Whenever you get a chance to visit your physics lab, you may try to measure the EMF of a cell, first by a voltmeter and then by a potentiometer. Comparing the two results, you may find the difference and you will be able to appreciate the instrument potentiometer. Happy learning. Thank you.